Hey, so welcome to the Amino Acid Show, and this show is going to be featuring just 4 of the 20 amino acids, and those amino acids are histidine, proline, glycine, and cysteine. And these 4 amino acids deserve sort of an extra time in the spotlight because they each have a side chain that sort of sets it apart from the rest. And so let's go through one by one and see what exactly these side chains are all about. And so first up we have histidine, and I've drawn the structure of histidine for you here. And here is the backbone of the amino acid. So this is the same for all of the amino acids. And then you see here is the side chain of histidine. So what is so special about histidine then with this side chain? Well, as it turns out, this side chain has a pKa of around 6.5. And this turns out to be really close to physiological pH, which is right around 7.4. So what does this really mean to have a pKa that's close to physiological pH? Well, recall that at a pH below an amino acid's pKa, the amino acid will exist in a protonated or positively charged form. And at a pH above an amino acid's pKa, it will exist in deprotonated form. Now, since the physiological pH, which is the pH of the fluid within our own bodies, is roughly equal to the pKa of histidine, then histidine is going to exist in both protonated and deprotonated forms. So this makes it a particularly useful amino acid to have at the active site of a protein, where it can both stabilize or destabilize the substrate. So next up we have proline and glycine. If we go ahead and take a closer look at proline, we have the backbone structure here, just like all the other amino acids, but then you can see that the side chain is this alkyl group that wraps around and forms a second covalent bond with the nitrogen atom of the backbone. And so we say that proline has a secondary alpha amino group. And so this is just referring to the fact that the side chain forms a second bond with the alpha nitrogen, the nitrogen in the backbone of this amino acid. Now let's come over here and take a look at glycine. Here we have the backbone of the glycine molecule, and then here we have the side chain. And the side chain for glycine is the simplest of all side chains. It is just one hydrogen atom. And I've drawn it out in wedge and dash form here to help emphasize how, because the side chain of glycine is a hydrogen atom, you have a duplication of atoms coming off of this carbon here, the alpha carbon. And so now this carbon is no longer a chiral carbon. So we'll write that here. No chiral alpha carbon. And this kind of sets it apart from the rest of the amino acids because the rest of the amino acids do have a chiral carbon, meaning optical activity under plane polarized light. And glycine is also considered to be very flexible because it just has this little hydrogen atom as its side chain, and so there's a lot of free rotation around this alpha carbon. So we also consider it to be very flexible. So why are these 2 amino acids grouped together? Well, they both play a role in disrupting a particular pattern found in secondary protein structure called the alpha helix. And an alpha helix is just a coiled up polypeptide chain that kind of looks like this. Now, because of its secondary alpha amino group, proline introduces kinks into this alpha helix, and it ends up looking like this. And also, since glycine is so flexible around its alpha carbon, it tends to do the same thing. And thus, both of these amino acids are known as alpha helix breakers. So last but not least, we have cysteine, and here's the backbone again. And then here is our side chain, and the side chain for cysteine has a special thiol group. And all thiol is really referring to is the sulfur and the hydrogen at the end there. So cysteines have this neat little trick where if they're in close proximity with each other within a polypeptide chain, or even between 2 different polypeptide chains, then their side chains can form a bond together between the 2 sulfur atoms called a disulfide bridge. So let's bring up 2 cysteine amino acids here. And I've shown them as isolated amino acids, but remember that they are part of a greater polypeptide chain. And the formation of the disulfide bridge occurs separate from the backbone. It is just between the side chains. The cysteine at the top is flipped over to bring its side chain in close proximity with the second cysteine below it. And then the bridge forms between the two sulfur atoms. So before we go over how a disulfide bridge is formed, let's do a quick little review of redox reactions. And really what you want to remember is the mnemonic oil rig. And that's to remind you that in oxidation you have a loss of electrons, so oxidation is loss. And in reduction you have a gain of electrons, so reduction is gain. So remembering that will help you understand the disulfide bridge formation. So going back to our two cysteines, if you look closely at their side chains, the thiols are existing in reduced form. So you're going to find these thiols in a reducing environment. Now, say those cysteines end up in an oxidizing environment. In that case, you would see the loss of these hydrogens and then the formation of a bond between these two sulfur groups, which looks like this. So this here is your disulfide bridge. So when do you see cysteines going solo, kind of like you see here in the separate thiol group form? And when do you see them forming these disulfide bridges? Well, it turns out that it depends a little bit on what the rest of the environment around them is like. And as it turns out, the exterior of the cell, or the extracellular space, is an oxidizing environment. So I'll write that down here. So the extracellular space will favor the formation of disulfide bridges. But in the intracellular space, you're more likely to find a reducing environment. So I'll write that down here. And the way that I like to keep this straight is that I kind of think of how the interior of the cell has these little molecules called antioxidants. And these antioxidants, which you can kind of tell by the name of it, stifle any oxidizing reactions, and so they keep the intracellular space a reducing environment. So you might have seen cysteine spelled without an E like this. And you're probably thinking to yourself, is it cysteine with an E? Is it cysteine without an E? Is it cysteine? Which one is it? I'm so confused. There are actually two official ways of spelling cysteine. The version with the E refers to cysteine when it's in its reduced form, and the version without the E refers to cysteine when it has been oxidized. And the way I remember this is by picturing that the E stands for electrons, and so you have the electrons when you're in the reduced form, and then you don't have the E for electrons when you're in the oxidized form. So hopefully that helps you keep things straight a little bit.